We will start our study of wave energy by looking at how waves are generated. Most of us have experienced waves in a pleasurable situation, on a beach for example, where breaking waves are beautiful and provide recreation for surfing and other sports. But waves are generated at sea, and mariners have long known their power. The photo on the right shows a ship of the U.S. National Oceanic and Atmospheric Administration in a storm off North Carolina in the Atlantic Ocean. Most of the NOAA research ships are on the order of 67 meters long, to give you an idea of the size of these waves. Let's start with some definitions. Everyone is familiar with the basic sine wave from physics. We have peak-to-peak amplitude. With water waves, that's called the wave height. The maximum height of the wave is called the peak of the wave, and the minimum height is called the wave trough. The wavelength is the distance the wave travels in one cycle. Continuing with the definitions, this illustration shows a simple wave traveling with velocity v. So we've added a third dimension to the wave. And let me call your attention to a very important dimension here, which we'll make reference to extensively. That is the wave crest length. So normally it's the third dimension. It's the dimension of the wave into the plane. Typically we're looking at a cross-section of a wave. And so later on, when we find out about wave energy conversion devices, typically the amount of power they can capture, or the amount of power in a wave, is specified per unit length, per unit wave crest length. So a very important parameter to keep in mind. So here we have a wave with wavelength lambda propagating with a wave velocity v, and we have a water depth here, which can be important under some circumstances. We characterize the wave in addition to its wavelength by the wave period, which is the wavelength divided by the wave velocity v. So the period is the time for successive peaks to pass a fixed point. And of course we could also specify the frequency instead of the period. It's simply inverse of the period. In waves we typically work with wave period, water waves. Alright, now that's a simple sine wave, but the ocean is really a combination of many waves altogether. I like to think of it as a stew of waves. So to get some idea of how this works in practice, let's just look on the left at two simple sine waves that are out of phase with each other. And while each one is regular, if we put the sum together and think of the sum then as being the motion of the surface, you can see now we get quite an irregular heights and troughs from the interaction of two components. If we add a third component, a higher frequency one, now you can see we've got a lot of chop on top of the waves, and so you can now get some idea of real waves, which not only have different phases and different heights, but also different directions. So the picture on the right shows another NOAA ship on the Georges Bank in the North Atlantic Ocean, and you can see that the ocean is highly irregular. The waves are very disordered here. Mariners have been dealing with waves for a long time, and so they've in fact come up with their own code for characterizing waves. So sea state codes 1, 0 through 9, and you can see a corresponding height associated with each code. I show this just to illustrate some descriptive characteristics of the different wave heights, so that you can get some physical intuition for this. So I particularly like some of these descriptions. So here we start with rough, very rough, high waves, very high, and phenomenal. That's certainly something you wouldn't want to experience on a ship. The World Meteorological Organization, WMO, also characterizes sea swell. And so you can see in the right-hand column there reference to essentially the period. So we have short or average or long, so descriptive of the time scale of the waves. Again, like the ninth characteristic here, confused, which is reflecting this often a storm situation where waves are coming from every direction and the sea is just a foaming mess, which has no really observable pattern. Okay, so with some background of definitions now and commentary, let's talk about wave generation. So where does a wave come from? Waves are actually generated, well, there are actually several sources of waves. First of all, seismic events produce long wavelength waves, and even the tides themselves are a very, very long wavelength wave. But for the purpose of harvesting energy from waves, the waves of interest are those generated by wind. So the figure shows wind acting on water from a shoreline on the left, and you can see from the arrow, which represents the wind, the longer the wind acts on the water, the greater the wave size. So the distance the wind acts on the water is called the fetch, so that distance is indicated by the green lines. Now this process doesn't go on forever. Eventually the wave formation processes are balanced by wave dissipation, energy dissipation mechanisms, and the wave reaches a fully developed state. Okay, so the right hand side of this, we could say, represents the fully developed state, and at that point the wave does not grow any further. So we can say that a long fetch and a long duration wind can generate fully developed waves. In practice, this rarely happens. So now let's talk about the wave generation process. The details are not fully understood, but there are three main processes that contribute. So first of all, air flowing over the sea exerts a tangential stress on the water, a shear stress on the surface, resulting in the initial formation and growth of waves. We have turbulent airflow close to the surface, which, as the wind speed picks up, creates rapidly varying shear stresses and pressure fluctuations. And when those pressure fluctuations are not in phase with existing waves, then the waves grow further. So it enhances wave growth. And then finally, when the waves have reached a certain size, the wind can exert a stronger force on the upwind face of the wave, causing additional wave growth. Right, so you can see that the mechanisms, different parts of different mechanisms have a stronger influence depending on what the size of the wave is. They all play a role. Now, a key point to remember about all this is that energy is transferred from the wind to the wave in each step of these processes. So now let's talk about wave size a bit, and the wave size, as you can guess from the figure we looked at, depends on a couple of things. Obviously the wind speed. The higher the wind speed, the more energy you might expect is available to generate waves. The duration that the wind blows, so if the wind dies out, then obviously the energy source has gone away. And then finally the fetch, the distance over which the wind energy is transferred into the water to make waves. Now there are a number of secondary effects as well. So not only the distance the wind acts on the water, the fetch, but also the width of that interaction area can have a secondary effect. The water depth can be important, and where the water is shallow, the bottom characteristics are important. They influence the friction, which is a dissipation mechanism. On the air side, the atmospheric stability is important. That influences the interaction between the wind and the waves. And finally, in the wind field, which is acting on the water, any temporal and spatial wind variations will also have an effect. So lots of things influence the wave size, but the three on the left are the primary factors. A couple of additional definitions. We talk about storm waves as being waves that are within or close to areas where they are generated. So that's sort of a special category. Swell waves are waves that travel out of storm areas with a minimal loss of energy, and these waves can go really great distances. And just a note that as you approach a shoreline on the continental shelf, the reduced depth can lead to a loss of power. We've seen that waves are generated by wind. In part A of the course, we learned that the sun is ultimately the source of the wind. So the energy in waves ultimately comes from the sun. Just to put some kind of numbers. If solar energy with 100 watts per meter squared average insolation can eventually become waves with power levels of 100 kilowatts per meter of crest length, right? So what we see from this process is we can see concentration and indeed storage of energy, storage in the sense that the wave energy appears quite some time later. Interestingly enough, the time lag gives some level of predictability. So we have a great deal of difficulty predicting wind, but once the wind starts to act and generates waves, we can actually predict the arrival of waves fairly well. So in terms of planning for the utilization of that wave energy, that knowledge of the timing of the energy arrival is quite helpful in getting good utilization. So if we know that waves are generated by wind acting over long distances, then where would we likely find powerful waves? This slide is reproduced from the very first lecture of the course, Part A, on wind, global wind sources. So we have a slide of the trade winds, and so what we're looking for are where are there long fetches with high winds. All right, so the westerlies are particularly good in this regard, and so you can see here from the Americas over to the UK we have a very long fetch, and so that might be a prime candidate for waves. We can see southern Australia is amazing. You've got winds acting for huge distances here with no intervening landmass, and similarly on the west coast of South America. This is a very interesting slide provided by NASA. It's on the left-hand side, wind speed measurements average over a 9-day period for the globe, and on the right-hand side, these are taken from a satellite, and on the right-hand side, corresponding wave height measurements made at the same time. So just a general sense, looking at the color comparison here, you can see that there's a really strong correlation between where the wind is and where the high waves are. So once again, this emphasizes the southern oceans where there's not much interference by landmass, very high winds here and very high waves as well. So that information about waves is summarized very nicely in this wave energy resource map, and what you're looking for here is the regions with high potential. So the three highest wave energy categories, if you look at the legend right here, are the yellow, orange, and red, and you can see the prime locations where those colors appear. We also need to be somewhat near a shoreline to be able to harvest the energy. You have to get the cables ashore. So we can identify quite a number of places here which are prime candidates for wave energy. So starting from the left, we have the Pacific coast of Canada and parts of the northwestern United States and Alaska. We have the western coast of South America. That's certainly known as a windy area in mariners' history, marine history. We look at the North Atlantic again, Iceland, the UK, and some parts of the western coast of Europe. We go to the tip of South Africa, and then finally to southern Australia, which you can see has really got tremendous wave energy potential. Okay, so that in a nutshell, we've learned about where waves come from and where they appear to have great potential. So let's summarize a bit. So waves are generated by wind. Since the sun is the energy source for wind, it is also the ultimate energy source for waves. We can characterize waves by a wave height, a wave period, and by a wave propagation velocity. The energy contained in a wave, or the size of the wave, actually depends on the wave's wind speed, the wind duration, and the distance over which the wind interacts with the water, which we call the fetch. And finally, the wave energy is strongest at a few locations where the wind travels over a very long ocean reach before reaching a coast. Due to the nature of the material, there aren't any specific practice problems that I can provide, but let me just pose a couple of questions for your thought. So, what is the prospect for wave energy in your location? The lecture is focused on oceans. What about waves in lakes and other bodies of water? Perhaps these are questions that you could share your thoughts on a discussion board in the course.